Some of the things that are done in the name of science these days would really make your hair stand on end. I'm hanging around, hoping I don't get too small for my boots, and just to show that Isaac Newton doesn't have to win all the time. But what's happening here is standing preconceived notions of engineering and a few other things on their heads, because what is bringing the colour to my cheeks... Good morning, Laura. What is bringing the colour to my cheeks and preventing me from plunging to an early death is glue. But the fact of the matter is that for modern adhesives, sticking a 12-stone man to the ceiling is no great problem. You should see some of the things they do.
Already, glue holds together anything from a racket to a rocket.
You come across adhesion or adhesives in almost everything that you buy, almost everything that's manufactured or made will use adhesives.
I think most people would be very surprised to find, for example, that in an aeroplane, much of the structure is bonded together.
A good example, perhaps, is your motor car. Your motor car is painted, which has to adhere to the metal on which it's placed. Inside the car, the upholstery will generally be stuck together with adhesives.
Rather closer to the ground, in the case of the car, all the brake shoes are bonded together. And so every time you've got to stop, particularly in an emergency, you're literally being held back by a layer of glue. And I think most people don't realise that.
Well, I think a lot of people would be less happy for knowing that, wouldn't they, than if they thought it was riveted.
Well, I feel more happy for knowing that. I must take a contrary view, because rivets impose such a high, intense point load that, in fact, things tend to break up round rivets.
Dr. Bill Lees is an adhesives chemist and a glue enthusiast, and it's certainly not the feeble stuff it used to be.
This is the bottom bracket of an aluminium bicycle. And by building in aluminium, you can actually reduce the weight of the aluminium involved relative to steel by 30%. So it's a much lighter bicycle. And here, if you take these forks, for example, in order to spread the stresses more correctly, the bottom lugs here, which are actually cast aluminium, have been bonded into the bottom of the fork itself. And if you go to the upper end of the fork, this joint is bonded, that joint's bonded, and this joint is bonded. To hand weld a racing cycle that this actually is takes about 30 hours, and in fact it can be cut to about an hour and a half by bonding.
No wonder glue is spreading. Professor Edgar Andrews is head of the Adhesives Research Unit at Queen Mary College, London.
Really, adhesives are to be found almost everywhere we go in our modern world. Of course, man didn't invent adhesives. Adhesion is found everywhere in the world of nature also. Think of spiders, for example, using adhesive threads to spin their webs and to stick them and to catch their prey, of course. Think of limpets and other shellfish that use adhesives to anchor themselves to rocks, seaweeds, and many other things, employ adhesives for this reason. Many insects stick their eggs in safe places under a suitable shady leaf. Generally speaking, adhesion is widespread in the natural world, so it was thought of long before we got into the act.
In the Menai Straits, Dr. Graham Walker grows barnacles for his research at the University College of North Wales. He's trying to measure the strength of their natural glue. They produce a two-part adhesive that anchors them in place.
Well, we seed them in the laboratory. Because they're an intertidal barnacle, we bring them out on the raft here where they're totally immersed all the time, and then they're able to grow to their maximum effect.
And how long have these been here?
These are 1 year old.
And then from here?
From here we take them into the laboratory, and there we pull them.
The barnacle shells are heaved from their slate bed and the forces involved carefully measured. The research is aimed at developing surfaces that barnacles won't stick to because they make boat hulls, oil rigs and pipelines harder to inspect and more difficult to maintain. But they certainly demonstrate that if you design the joint properly, then glues can take enormous strains.
Here comes one barnacle.
The barnacles make sure that they put their two-part glue where it will resist the forces that try to remove them from their rocks. And engineers have to imitate them.
Mix this well together.
This one-man-power test shows that if you just try to pull the glued joint apart, it will take the strain.
The joints are about equally strong.
But peel it, and it can't cope. But failures, even those caused by bad design, put engineers off. So how to convert them?
It's a question of education, and the fact is that nowhere, almost in the world, are engineers taught adhesive technology. And indeed, the subject of adhesive technology is only taught in 1 or 2 centres. And so the chaps are actually working with materials that they are not very familiar with. The result of this is they usually have a bad experience, and as a result of that bad experience, all glues are damned.
You don't have to go into industry to find adhesives. There are plenty of things in the home that will stick perfectly, adequately. You and I think of this sort of thing as a damn nuisance. I suppose scientifically speaking, it's the result of an intimate molecular association between 2 dissimilar materials. Because that, in fact, is what bonding, adhesives, is all about. They depend on the same forces that hold you and me together to stop us flying apart, to stop this pan flying apart, to stop any of the things around us flying apart, because the forces of the atoms that make them up are holding them together. And that really is the whole secret of making an adhesive. You have to find a material which will form an intimate bond with one surface and an intimate bond with the other surface, so that when they're brought together, the adhesive, the film of adhesive in between them, as it were, overcomes their natural reluctance to have anything to do with one another. There are, of course, plenty of materials, fortunately for industry, which are very happy to bond with one another, whose surfaces are quite happy to be associated. There are also, fortunately for the cook, some surfaces which are extremely reluctant to associate, and this pan, which has been coated with PTFE, is obviously very reluctant to associate with the water I've poured into it. It just stands about in drops, and it would have been equally reluctant to accept the spaghetti. If only I'd used that in the first place, I could have saved myself a lot of trouble. Another job for father. It isn't one thing and it's another. Trouble is, you never know what's going to break next, do you? I should imagine that the modern adhesives industry comes to my rescue 3 times a week. Of course, all these glues have very fancy ingredients in them, with names like cyanoacrylate or formaldehyde or phenolic. But we've had glues for many thousands of years. The Egyptians used to stick things with the white of an egg or with blood, and we've traditionally made glues out of melted down animal bones and fish bones. And my father used to hang wallpaper with a paste made from flour. And in the early days of flying, they used to stick their wooden aircraft together with a glue made, believe it or not, from skimmed milk.
This government scientist works on the use of glues in the latest aerospace applications. Work that stems from the shortcomings of those natural materials.
The casing glues are a product of skimmed milk, and they're attacked by bacteria. And it's a very good non-destructive test of a wooden aircraft bonded with the casing was when you smelt old Camembert cheese, you knew your adhesive had gone off.
Your plane was likely to fall to bits in the air, was it?
Leslie Mitchell reporting. The story of the DH-98, or Mosquito, is one of brilliant success. The stressed skin fuselage, proved by the Albatross in 1937, has been proved again by the Mosquito. While I wouldn't like to say that anybody could build a mosquito, its construction is very widely dispersed. Many furniture and other woodworking factories, large and small, have been turned over to the job. If it's to be furniture or mosquitoes, Britain, for the time being, prefers mosquitoes. And how it flies. The mosquito has certainly gone far to prove that British designers and Royal Air Force pilots will continue to make rings round the enemy till the war is won.
But the early mosquitoes were successfully bonded with casein adhesives. But urea formaldehydes came in the late 30s and were used during the 40s considerably for wooden joints and have been used consistently for wooden bonding since, really.
It was at Duxford, near Cambridge, that the first synthetic glues for the aircraft industry were made in the 1930s. Ted Garnish, adhesives chemist with the international company that makes them today, harks back to those early successes.
It was a continuation of design principles that had been established earlier. Aeroplanes then were made of wood, but they'd been stuck together with glues, with naturally occurring materials, which were always susceptible to difficulties with environmental resistance. Microorganisms like to eat natural glues based on gelatine or blood or fish glue, just what they like to eat indeed. So something synthetic was needed. Also at the same time, aircraft design was beginning to go through a revolution. People wanted to make more efficient structures, lighter structures, start using metals for aircraft. So it was a period when there were great changes in the wind. I mean, we're talking about the period of 1935 up to 1939, so there were other pressures as well.
The war accelerated the technology, and the great step forward was to bond not just wooden, but metal aircraft too.
The first structural adhesives for metal bonding really came in the early 40s, invented by Dr. de Bruni, and these are based upon phenolic adhesives, again a completely synthetic adhesive, but using a thermoplastic component because they tend to be very, very brittle otherwise. And this process, which came in the 40s, was first used for metal-to-metal bonding on planes like the Sea Hornet, which were late 40s aircraft, but have been used consistently ever since, and have given very good performance, and they're still widely used in the aerospace industry.
Has it been shown over the years that glues in aircraft can take anything that gets thrown at them?
Oh yes. In fact, the most ironic instance of that occurred with the comet disasters in 1950-1960.
This is the tragic scene of the comet disaster near Calcutta. Wreckage of the aircraft smashed almost beyond recognition. At the time of this terrible accident, the aircraft carried 37 passengers and a crew of 6. All lost their lives. The first fatalities of the Comet passenger services, which had previously carried 28,000 passengers safely.
It was proved by an investigation at Farnborough and by salvaging wreckage that the bonded line had not failed. It was a fatigue failure around more conventional methods of joining. That was a rather horrific experience, but it graphically highlighted the advantages for this sort of construction.
The use of glue has been a major factor in the development of modern aircraft. It's made possible aircraft that are bigger, lighter, and stronger. At Hatfield, British Aerospace is gluing together a very large proportion of its new high-winged jet, the 146. The alloy components emerge from bath after bath of often aggressive chemicals in an elaborate preparation that's to ensure a good bond. Long strips of phenolic adhesive film are held in place with dabs of a less exotic glue applied to the stiffening ribs of a fuselage panel. A huge jig makes sure that everything's in the right place. The fuselage skin is lowered onto the ribs, sandwiching the phenolic before the complete, but not yet bonded unit is fed into an enormous heated press. What comes out of it is an equally enormous piece of aircraft. Very light, very strong, very fatigue resistant, and with never a rivet in sight. British Aerospace's chief structural engineer on the project is Frank Vann. As we clambered through the unfamiliarly bare passenger compartment, I asked him how hard it would be to make the modern jet without adhesives.
Well, we believe that using bonded structures saves weight, and it also improves the fatigue life of the aeroplane, because the rivet holes in normal construction are all initiators of fatigue problems, and you eliminate all that with the bonded structure.
So do you use adhesives everywhere, or some places you use them and some places you don't?
Well, in general, we use adhesives wherever we possibly can, with one or two exceptions. One, as you can see here, if you look in the bottom of the fuselage, in service, fluids collect in the bottom of the aeroplane from condensation and leakage from toilets and galleys. In that area, there's an increased corrosion problem, and so we tend to use Z-section stringers, which are easier to inspect, and also the adhesives don't stand up very well to that sort of environment over 20 years. So the stringers in the centre section of the fuselage there are riveted.
Presumably, though, you have enormous confidence in adhesives, otherwise you wouldn't be using them.
Well, we have, yes, because our experience has shown that's justified. We've recently cut some bonded joints out of the Comets, which have been in service for over 20 years, and retested them, and the results that we've got are just as good as they were on the day the aeroplane was built.
As a man who stakes reputation and lives on glue, Frank Vann is a little puzzled by other engineers' reluctance to use it, but then could say a motor car be stuck together.
I don't see any reason why it shouldn't. A structure of a motor car is no more difficult to build than the structure of an aeroplane. In a lot of ways, a lot easier, I would think. And I don't see any reason why adhesives shouldn't be used in car design.
And if you were bowling along the motorway and your driver turned to you and said, "This car's stuck together," how would you feel about that?
Wouldn't worry me at all. I fly in aeroplanes that are stuck together.
It goes without saying that pretty well every modern aircraft is hand-built, an exotic, exclusive, expensive branch of engineering. And you can't help feeling that if adhesives are really going to grow up, it's going to be in the mass production industries, which in this case means the motor car. A number of car manufacturers are already researching the possibility of a bonded car, especially those who want to use plastic or alloy bodies. Frontrunner in the UK is British Leyland. They already make this Triumph Acclaim. Quite a number of components on it are already bonded, and there's one that's very easy to look at and well worth seeing. This is the main framework of the boot lid, perhaps not the most important part of the car, but a very significant one in this case. These blobs here are not the results, as you might have anticipated, of spot welds, but they're caused by putting a little dish into the metal. And a blob of adhesive has been put into that to bond the skin onto the main framework. That adhesive wasn't put there by human beings either. It was put there by a robot gluer, another significant advance for adhesives in industry. In fact, there are only 2 spot welds in the whole of this construction, and they're hidden. There's one there, and there's another one there, put there to hold the frame in place until the glue sets. And the fact that they make a dimple in the metal at all may mean that the days of the spot welder are numbered. What the motor industry has been waiting for is an adhesive that can be applied in the same way spot welds are made, that's less fussy about preparation than those the aircraft industry uses, and that will stand up to the various forces that are generated in a crash. Well, the answer's arrived. They're the Toughened adhesives. This test piece is glued together with a toughened epoxy, a glue that has molecules of rubber combined with it. Its look-alike is stuck with the sort of stuff that fixed my boots to the ceiling. The sample is screwed down and a weight swung at it. The impact will be equal to a 1 pound weight landing after a 40-foot fall. The adhesive bond is just 1 inch square. The first sample shears off. The glue is cracked along the joint. Now the second sample, with the rubber in the glue that's intended to absorb the shock to stop the cracking. It does. 1 square inch of adhesive stands up to a sledgehammer blow. More realistically, this is a typical load-bearing box section from a lorry or a car, except that it's made from aluminium and it's glued together. As the test load goes up and up, it buckles and bends, but the joint doesn't fail.
If motor engineers are going to build extremely lightweight vehicles, they have simply got to use adhesive. The only other way you can make cars lighter is to use either aluminium or plastic or very, very thin sheet steel. But this then gives you corrosion problems. In between the welded points, you have small areas of metal where there's air and water can get in, and unless you paint it extremely carefully, this is a natural water trap and corrosion starts there. And if you look at most cars, you'll find that they're always corroding around the welded seams. Now, if you replace welding by bonding and you fill all of those gaps, then water can't get in, air can't get in, and the natural processes of corrosion are inhibited. And if you bond it, corrosion problems are reduced. If you bond it, the high stresses associated by individual weld points is reduced, and you can't put steel to aluminium. I mean, it's impossible to weld steel to aluminium, so the only way you can put it together is to bond it. Similarly, you can't put plastic to aluminium or plastic to steel. The only way you can do it is to bond it.
The 1982 British Motor Show. A brave smile on the face of a worried industry, with individual manufacturers fighting to keep their share of the market. But the struggle isn't all bad news. The silver lining is that the motoring public is being offered better value for money and more miles for fewer gallons. But what's the connection between fuel economy and adhesives? Easy. The motor manufacturers are very aware that a lot of the market could be scooped by a car that did, say, 75 or even 100 miles to the gallon. But to achieve that, you've got to build a car that isn't just mechanically and aerodynamically efficient, but much, much lighter. To build a lighter car, you can do what some of the manufacturers, the Japanese amongst them, have done, and that is to use high tensile steel in thinner section and get the weight down that way. But in the end, you've got to forget mild steel and go for aluminium or plastics. And you can't readily spot weld either aluminium or plastics, so you've got to make not a welded car, but a bonded one.
Now, British Leyland have done just that. This is the ECV3. Plastic panels on an alloy frame mean dramatic weight savings to give an astounding 61 to the gallon at 75 miles an hour. It's only possible because of the glues that the British technology of Bill Lee's firm has developed. Roy Brocklehurst is head of experimental vehicles.
This vehicle is little heavier in curbside trim than a Mini, and of course it is a 5-seater. What we find with adhesive bonding is that we can get up to a 50% improvement in torsional stiffness of the body shell. The aluminium is virtually corrosion-free. The plastic skin panels are low impact resistant.
So do you think that we can expect to see the bonded car becoming not just the prototype that this is, but a pattern for the future?
The hurdles that we yet have to get over are related to volume production. But I think by the end of the decade, I'm sure that we'll be seeing an awful lot more bonding.
Well, whatever this car achieves in terms of fuel economy and corrosion resistance, it's proved one thing already, that adhesives have come of age. Like the bonded bike, the bonded plane, the bonded car is on its way.